Today is December 21st, 2022. This is my 168th episode for C++ 17 2023 CUDA SQL OpenCL DBB Balkan. We will discuss implicitly defined functions, derivatives of higher order 4, second order derivatives 1. I will film 1 or 2 more videos about second-order derivatives. We need 2 books, Thomas's Calculus 13th edition and Calculus by James Stewart 9th edition. Warning: do not download these PDF books if you do not own your legitimate hard copy. Don't degrade yourself into a pirate just to save a few dollars. I have given my warning. If you click this link, you can download Thomas's Calculus 13th edition and the Calculus by James Stewart 9th edition. The zip file contains Calculus by James Stewart. I have 4 copies of this book. Also, I have 6 copies of Thomas's Calculus. This is 13th edition, This is 10th edition. These are 14th edition. If you do not have legitimate hard copy, then don't use this link. Or if you use this link, then purchase your own legitimate hard copy. I have given my warning. Don't degrade yourself into a pirate just to save a few dollars. I assume you have watched my previous videos listed here, especially from episode 164, Implicit Derivative, Extended Newton Method, up to episode 167, Derivatives of Higher Order 3, Generalization, and the Function Generator. Please double-click this link. From episode 167, Implicitly Defined Function, Derivatives of Higher Order 3. Show more. Download current video source code. Please click it. Show in folder. Unzip it. Rename 168. Copy. Paste it in your working directory. Open up Visual Studio Code. C++ 17 2023 parallel. From folder 168, open newton.cpp. Ctrl B. I assume you have watched my previous video, episode 167. Also, I assume you have Thomas's Calculus 13th edition and the Calculus by James Stewart 9th edition. Now, Ctrl End. Scroll up. From here, copy this part. Ctrl End. Paste it here. I will change the function name. Test second order derivative theory. Copy this function name. Paste it here. Disable it. In this episode, I got the theory from this book, Calculus 9th edition, James Stewart, chapter 14.5, the chain rule, exercise 14.5, problem 60, page 994. From this book, Calculus by James Stewart. This is 9th edition. From this book, page 994. In chapter 14, partial derivative, page 994. Problem 60. we use this formula. In calculus, we need first order derivative, usually mean velocity. We also need second order derivative for acceleration. We also need third order derivative. If acceleration is constant, then third order derivative gives 0. If you can derive second order derivative, that means you understand chain rule correctly. From Thomas's Calculus, 13th edition, page 175, exercise 3.7. If you scroll down, you can find second derivative. In exercise 21 through 26, use implicit differentiation to find dx over dy, then second order derivative with respect to x. We will use this problem, unit circle, to understand the theory of second order derivative. So, the theory comes from Calculus 9th edition, James Stewart, problem 60, page 994. Our example comes from Thomas's Calculus 13th edition, exercise 3.7, problem 21, page 175. We are going to solve unit circle. So, order f, order x, order y. Return x square plus y square minus 1. This is unit circle. We also need, using CPG numerical analysis, comments. Since this is unit circle, we need a point on circle. For such purpose, we will let order x 0.4. X and y should be less than or equal to 1 because we are using unit circle. Or we let y 0.0. Y is unknown yet. Or y range can be CPT make array. This is a function from negative 1.0 positive 1.0 because we are using unit circle. X and y should be less than 1 or greater than equal to negative 1. We will use split count 10. This split count is arbitrary. If your solution fails, then try to change this value. We need to solve values of y. So, order solution y. CNA extended Newton method. We are solving this function with respect to y. So, solve for y. This constant is defined here. Solve for y in the holiness.hpp. Now close it. We pass split count. Then y range. Then this implicit function f, then x, y. We have to solve our solution first. SED, C out, solutions of y with x, x. Then solutions y, CPG, and L. Now we solved the values of y. We will copy this function name in the function main. We can use any compiler. CD 168 Newton Clang++ SED C++ 20 Newton.cpp LTBB 12 or C.exe. Sorry, scroll up. I missed namespace. We build again. CLSC. When x is 0.4, the values of y are given like this. If we change, for example, 3, then we can try. See if x is close to 1, then CLSC. We have 2 negative 0.6, 2 positive 0.6. I will prune out or filter out or remove redundant or superfluous values. Please understand, I created this function was created in a rush, neither performant nor accurate. I will improve this function in the future sessions. Go to declaration. This function calls Newton method. This function. In this function, I use set to sort solutions. I used SCD set to sort solutions, but SCD set is not very performant, so I will modify this function in near future. Scroll down. We return result. Result is a vector. We will filter out superfluous or redundant values like this. Or for SED unique. Result, begin, result, end. Here we provide predicate like this, or x or y. Curly brace. I will give line break here, line break here. Context per or epsilon. We use epsilon for Newton method. We have to provide the element type ARG type here. This is function. Then return std abs x minus y should be less than epsilon. This lambda returns Boolean value. Such function that returns Boolean value is called predicate. Please remember this term. Now we can say results erase. We use for, then results end. But this is dangerous practice. We need safeguard. If for is not equal, results end. Okay, we have to do like this. About such things, I will explain when I optimize Newton method. With this, we try again. CLSG. Now we removed redundant values. We also need to check with the Intel compiler. CD 168 Newton ICPX STD C++20 F no sickle Newton.cpp or i.exe, hit enter. CLS I. So Intel compiler also works. Now in Thomas's calculus, this is exercise 3.7 problem 21. We will check answer sheet. Answer to odd numbered exercise section 3.7 problem 21. So we are not interested in first order derivative. We are interested in second order derivative. With this, here STD cout algebraic solutions over second order derivatives CPG and L for oro YY solutions Y. We will copy this expression and paste it here. So negative y square minus x square over y cube. Let's double check. Negative y square minus x square over y cube. So this is correct. Now auto y prime we will copy this. It should be underscore 2. It should be underscore 2. We have to bind parentheses, then parentheses y cube semicolon. STD cout y 2 prime with x yy, this yy equals y pp cpg and L. Or I would say quote I fixed like this. Now SED Cout CPG and L. We build again. CLSG. Something wrong. Sorry. This is YY. YY. We rebuild. CLSG. So this is our solution. We can control the precision. I will disable it for the time being. We can build again. CLSG. Sadly, these values are incorrect. I made a serious mistake here. In this case, we have to do like this. Please be careful. This expression. Also, we use y outside of formula, but we can use y. This y is scoped inside of formula. This y is independent from this y. Here, it can be confusing. I will fix like this. We rebuild CLSG. This is correct result. Now, let's move on. Here, SED, Cout, numerical solution for second order derivatives, CPG and L. For all y solutions y. Now we need this book, Calculus, James Stewart, 9th edition, page 994. Problem 60. We will use this formula to evaluate second order derivative with respect to x. We need to evaluate partial second order derivative of f, partial first order derivative with respect to y, then with respect to x, then with respect to y. We have to evaluate all these partial derivatives. We need this book, Calculus, 9th edition, James Stewart, chapter 14.5, chain rule, exercise 14.5, problem 60, page 994. Now, step 1, order fx, CNA, partial derivative, dx1, we pass f, x, y. We are differentiating function f. once with respect to x. I will denote fx. In this book, we are evaluating fx or first order partial derivative of f with respect to x. Now, step 2, we differentiate fy with respect to y. Now, step 3, we differentiate fxx. We differentiate twice with respect to x. In this book, we are differentiating fxx. Now, step 4, this is step 4. We need auto command x, y, CNA, create command. We differentiate with respect to y once, then with respect to x once. So we created a command. Then it is fxy. Here we pass this command. It means we differentiate function f with respect to y once, then with respect to x once. So it is fxy. In this book, we are evaluating this term. Now, step 5. I will copy this, paste it here. This is fyy. We differentiate function f twice with respect to y. Then we can compute answer. We are using this formula. Copy, paste. It is very ugly. I will just delete. I say step 6. I will simply copy and paste. So this expression is equivalent to this. Now we display, scroll up. I will copy, paste it here. It is answer. Then std, cout, cpg, and there. We build again. clsg, algebraic solution of second order derivatives at point 0.8, negative 0.6. Second order derivative is 4.62963. 4.62963. In this case, negative 4.62963. Negative 4.62963. So, algebraic solution, numerical solution matches exactly. Please understand. Step 1, Step 2, Step 3, we can pass dx1, dy1, dx2. In case of Step 5, we can pass dy2 directly. In this case, we have to differentiate dy, then dx. In such case, we can use create command. Then we can pass this command. This algorithm partial derivative is super powerful. We will generalize second order derivative in my next episode. Please understand I made correction to this header file CPG calculus. I will upload updated C++ library extension to my file server. If you want to try this code, you have to download updated C++ library extensions. Now, I will give you your homework. Please understand, second order derivative is very important. Also, we need third order derivative. Third order derivative is used to test if second order derivative is constant because second order derivative represents acceleration. Constant acceleration is very important. In some cases, acceleration is not constant. Third order derivative is also used to evaluate torsion. When you derive this formula, y is dependent variable, x is independent variable. Keep this point in mind. You can read more theory about implicit differentiation, implicit function theorem. Read this explanation carefully. Also, in Thomas's Calculus, Chapter 3, 3.7, Implicit Differentiation. Here, you can find more examples. You can solve this problem. Also, this example, derivatives of higher order. You can try this problem and evaluate second order derivative. You can also try this example. In the exercise, second derivatives, you can try odd numbered problems. In such case, you have to pay attention to the domain of y. You can also try this problem. This is the same problem. Find the slope of the curve at given point. Of course, this is first order derivative. Make yourself familiar with second order derivative using implicit differentiation. In my next episode, we will generalize what we learned in this episode.